Welcome to another lecture on signal and system. Signal and system. So this is lecture number 16. So in lecture number 15 we have just started the LTI system. So the LTI system function. So what is system function basically? So we have discussed the system function. So for LTI system, if xt is the input, and ht is the impulse response, then yt is related to xt with xt convolution with ht. So basically we take the Laplace transform, taking Laplace transform on both sides and using the convolution property ys is equals to xs multiplied by hs. So basically what is happening that we have yt is equals to xt convolution with ht. So when we take ys, so basically the convolution in time domain is equals to the product in s domain, so it is equals to xx multiplied by hs. So what is happening here is that convolution in time domain is equal to the product in s domain is equals to the multiplication in s domain. So where xs, ys and hs are basically the Laplace transform of xt, yt and ht. So xt, the Laplace transform of xt is xs. We have yt, the Laplace transform of yt is ys. Then we have ht, the Laplace transform of ht is hs. So basically if we see the relation ys equals to xs into hs, then we can find out the system transfer function, that is hs is equals to ys divided by xs. So hs is called the system transfer function. So what is hs? hs is called the system transfer function. So it is basically the Laplace transform hs, of ht is referred to as the system function, system function. So or the transfer function, or it is also called the transfer function of the system. So if we write the proper definition, then we can write it as the system function hs can also be defined as the ratio of the Laplace transform of the output yt and the input xt. So the system function hs, the system function hs completely characterize the system because of the system impulse response, because of the system impulse response ht completely characterize the system, So there are some characteristics of the system function. So let us discuss some of the characteristics. But before that, many properties of the continuous time LTI system can be closely associated with the characteristics of transfer function in S-plane. So basically many properties of the continuous time LTI systems can be closely associated with the characteristics of HS in the S plane, and in particular with the pole, locations and and the ROC. So basically the pole location and the ROC characterize the system. So basically if we know the HS, then we can completely characterize the system. If we know the transfer function, HS, so HS will completely characterize the system, so this HS will completely characterize the system. Now this is input xt, this is impulse response ht, this is output yt. Now the Laplace transform is HS, the Laplace transform is xs, then it is Laplace transform of this ht is xs, then ys is nothing but xs multiplied by hs. Here yt is xt convolution with ht, then ys is equals to xs multiplied by hs. So this figure is basically, it is impulse response and system function. So it is basically impulse response and system functions. So there are some characteristics of the system function. So first let us see, study the causality. So let us discuss the causality. So for a causal continuous time LTI system, for a causal continuous time LTI system, for a causal continuous time LTI system, we have ht is basically equals to 0 for t less than 0, and since basically if ht is equals to 0 for t less than 0, so we are talking about the right hand sided signal. So since ht is a right sided signal, the corresponding equivalent in the corresponding equivalent in Hs is that of ROC of Hs must be of the form real part of S greater than. So the corresponding requirement in Hs is that the reason of convergence, the ROC, the reason of convergence of Hs must be of the form real part of S is greater than sigma max. The real part of S is greater than sigma max. That is the ROC, that is the reason of convergence, is the reason of convergence is the reason in S plane, to the right of all of the system, to the right of all of the system poles. So basically the ROC should be right to the rightmost pole. So basically we can say that the real part of S is greater than sigma max. So this is the condition, real part of S is greater than sigma max. So thus that is the ROC is basically, the ROC is the reason in S plane, to the right of all the system poles. So similarly Similarly, if the system is anti-causal, then ht is equals to 0 for t greater than 0, and ht is left sided, and if ht is left sided, okay, so then the ROC of hs, then the ROC of hs must be of the form real part of s is less than sigma minimum. Real part of s is less than sigma minimum. That is the ROC is the region in S plane to the left of all the system pose. So next is the B part is stability. Next part is stability. So continuous time LTI system is VIBO stable if and only if minus infinity to plus infinity modulus of ht dt less than infinity. So the corresponding requirement of hs is that the ROC of hs contains the j omega axis, that is S is equals to j omega. So let us discuss this characteristics. So let this is R1, this is the region of convergence 1, that is R1. So ROC is R1, and there is another ROC. So this is R2. Let this is R2. The ROC is R2. Now this ROC R1, this is sigma, this is j omega, this is sigma, this is j omega. So this ROC is containing the j omega axis. So R1 containing the j omega axis. So we can say that if this system is stable, the system with ROC R1 is stable, and this ROC is not containing the j omega axis, so we can't say that it is stable. It is unstable basically. So this system is stable because it is containing the j omega axis. So let us do one problem. So let us do the problem. If a continuous time if a continuous time LTI system is BIBO stable, then show that the ROC of the system function HS must contain the imaginary axis, that is it is equals to S is equals to J omega. So a continuous time LTI system is BIBO stable if and only if its impulse response HT is absolutely integrable, that is minus infinity to plus infinity HT dt less than infinity. Now HS is equals to minus infinity to plus infinity HT e raised to the power minus dt, then let S is equals to J omega, because we are talking about we want to find out the imaginary axis. So at imaginary axis the value of S is equal to J omega. So let S is equal to J omega, then we have Hj omega is equals to minus infinity to plus infinity HT e raised to the power minus j omega t into dt, then modulus of Hj omega is modulus of minus infinity to plus infinity Ht e raised to the power minus j omega t dt. Then it is equals to less than or equal to minus infinity to plus infinity modulus of Ht e raised to the power minus j omega t into dt, and it is equals to minus infinity to plus infinity Ht modulus of Ht dt, and it is less than infinity. So therefore we see that if the system is stable, then HS converges for S is equals to J omega, that is for a stable continuous time LTI system. For a stable continuous time LTI system, the ROC of HS must contain the imaginary axis S is equals to J omega. So next characteristics is very important, and it is causal and LTI system. Next characteristics is very important, and it is causal and LTI system. So if the system if the system is both causal, if the system is both causal and stable, then all the poles of HS must lie in the left half of the S plane, that is they all have negative real parts, because the ROC is of the form real part of S is greater than sigma max, and the time and since the j omega axis and since the j omega, because this S plane is basically we have converted to S plane our continuous time system. So since the j omega axis is included in the ROC, so we can say that it is so it is included in ROC. So we must have sigma max less than 0. So we must have sigma max less than 0. So this is the condition. So this is the condition when we have sigma max less than 0. Now let us discuss the linear system function for LTI system described by linear constant coefficient differential equation. So let us discuss the system function for LTI systems. System functions for LTI systems described by linear constant coefficient linear constant coefficient differential equation. Differential equations. So the system function for described the linear constant coefficient differential equations. So basically for the linear constant coefficient for the linear constant coefficient LTI system, we have summation k is equals to 0 to capital N ak dk yt divided by dtk is equals to summation k is equals to 0 to capital M bk dk xt divided by dtk. So this is our equation for linear constant coefficient differential equation for continuous time LTI system for continuous. So taking the Laplace transform on both sides, what we will get? So we will get, not taking, please wait, it is opening, please. Now taking the Laplace transform, on both sides, and taking the Laplace transform on both sides and applying the and using the differentiation property, of the Laplace transform, we obtain summation k is equals to 0 to capital N a k s raised to the power k y s is equals to summation k is equals to 0 to capital M b k s raised to the power k into xs. So what is hs? So hs is nothing but ys divided by xs, and it is equals to, from this equation, it is equals to summation k is equals to 0 to k is equals to m bk s raised to the power k divided by summation k is equals to 0 to capital N a k s raised to the power k. Now we can write hs as, hence thus hs, we can say that hs is always, so we can say that hs is always rational. Then we can say that hs is always rational. Now we have some system interconnection also, so we can we have some system interconnection. So for two LTI system, for two LTI systems with the impulse response h1t and h2t respectively in cascade, the overall impulse response ht, is given below. The overall impulse response ht is given below. ht is h1t convolution with h2t. So thus the corresponding system, the corresponding system functions are related by the product hs is equals to h1s multiplied by h2s. So we have input xt, then we have h1t and h2t, the output is yt. So it is replaced with single single impulse response, that is HT. So what is HT? HT is H1T in convolution with H2T, because they are connected in cascade. So if we take the Laplace transform, then the Laplace transform of xt is Hs. It is applied to the system function, transfer function, that is system with transfer function Hs, and Ys is the Laplace transform of Yt. So Hs is nothing but H1s multiplied by H2s. So we have applied a property here that the convolution in time domain is equals to the multiplication in S domain. So we have applied this property that the convolution in time domain, so this is the convolution in time domain, and it is basically the multiplication in S domain, So similarly the impulse response of a parallel combination of two LTI systems is given by HT is equals to H1T plus H2T. So thus Hs can be written as H1s plus H2s. So if we have input xt, then if we apply the input with the impulse response of first is H1t, and in the impulse response of H2 of second system is H2t, then this is the output Yt. So it is replaced with, it can be written as xt. We have a single impulse response of the whole system, and this ht is nothing but H1t plus H2t. Now if we take the Laplace transform, then it is written as Xs. We have H1s, then we have H2s, and the output is Ys. So the Hs is basically we can write in single transfer function form, that is overall transfer function form. So that is Hs is nothing but the H1s plus H2s. So this is our system in S domain, and then previous slide the system in time domain. So what is the conclusion? So if two systems, the conclusion is, if two systems are in cascade, then the overall system HT is H1T convolution with H2T, and if two systems are connected in parallel, then the system response is H1T plus H2T. So let us solve some problem. So find the Laplace transform. Find the Laplace transform and the associated ROC and the associated ROC for each of the following signals. So the first signal is xt is equals to del t minus t naught. Then we have xt is equals to ut minus t naught. Then third is xt is equals to e raised to the power minus 2t ut minus ut minus 5. Then xt is equals to summation k is equals to 0 to infinity del t minus kt. Then last part is x t is equals to del t plus at plus b. So a and b are basically real constants. A and b are basically real constants. So let us solve the problem. So part a is xt is equals to del t minus t naught. So if we draw xt, then we can find out that here is a delay t naught, and this is our unit impulse function now delayed at t naught. So xs is minus infinity to plus infinity xt e raised to the power minus st into dt by the definition of Laplace transform. So it is del t minus t naught e raised to the power minus st into st into dt. Now we can apply the property. If we multiply gt with del t minus t naught, what we will get? We will get gt naught del t minus t naught. So here we can apply here minus infinity to plus infinity del t minus t naught e raised to the power minus st naught into dt. So we can take e raised to the power minus st naught outside, and this is equals to e raised to the power minus st naught into 1. So ultimately the Laplace transform xs is e raised to the power minus st naught, and the ROC is basically all values of s. And the ROC, because if we see that convergence, then we can find out that ROC is the entire s-plane. So the ROC is entire s-plane. So let us solve the b part, that is xt is equals to ut minus t naught. So this is a unit step function delayed at some value t naught. So ut minus t naught is equals to 1 for t greater than or equal to t naught, and it is equals to 0 for t less than 0. So it is minus infinity to plus infinity ut minus t naught e raised to the power minus st into dt. So this is xs. Now it can be written as t naught to infinity e raised to the power minus st into dt, and the solution of this is e raised to the power minus st naught divided by s, and the real part of s should be greater than 0. So the ROC is real part of s greater than 0. Real part ROC is basically real part of s greater than 0. Now let us solve the third part. So it is xt is equals to e raised to the power minus 2t ut minus ut minus 5. So it can be written as ut e raised to the power minus 2t ut minus e raised to the power minus 2t ut minus 5 Now the Laplace transform is xs, that is minus infinity to plus infinity xt e raised to the power minus st into dt. So it is minus infinity to plus infinity e raised to the power minus 2t into ut minus e raised to the power minus 2t ut minus 5 e raised to the power minus st into dt. So it is equals to minus infinity to plus infinity e raised to the power minus 2t ut e raised to the power minus st into dt minus infinity to plus infinity e raised to the power 2t ut minus 5 e raised to the power minus st into dt. So this is xs. Now we can solve this. So the solution of this is xs is equals to 1 divided by s plus 2 minus e raised to the power minus 5 as plus 2 divided by s plus 2. And what is the ROC? So the ROC is very simple to calculate. It is real part of s. It is real part of s greater than minus 2. So basically if we see that, so we can combine this. So 1 divided by s plus 2, 1 minus e raised to the power minus 5 s plus 2. It is the Laplace transform, and the ROC is real part of s greater than minus 2. Real part of s greater than minus 2. So the ROC is, this is minus 2, the ROC is, this is j omega, this is sigma. The ROC is basically, this is ROC, that is real part of s greater than the real part of s greater than minus 2. So this is the ROC. Now we can see that the pole is at s equals to minus 2. So the ROC is not containing the pole. And also we can see that the ROC contains the j omega axis. So the ROC contains the j omega axis. So it is stable. So it is stable system. So it is stable because the ROC is containing the j omega axis. So basically it is a stable system. Now let us solve the D part. The D part is xt is equals to summation k is equals to 0 to infinity del t minus kt. Now the solution of this is xs is equals to minus infinity to plus infinity xt e raised to the power minus st into dt, and that is equals to minus infinity to plus infinity summation k is equals to 0 to infinity del t minus kt e raised to the power minus st into dt. So we can see that we can put the summation outside. Further we can solve this by using that property. So minus infinity to plus infinity summation k is equals to 0 to infinity. So k is equals to 0 to infinity del t minus kt e raised to the power minus skt into dt. Please check this. We have used the property, that sampling property we have used. So the solution of this is basically this e raised to the power minus skt we can put outside, and summation also we can put outside, and the integration of the remaining term will be equals to 1. So the series expansion is e raised to the power minus st into 0 plus e raised to the power minus st into 1 plus dot 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 up to infinity. So it is gp. So 1 divided by 1 minus e raised to the power minus st. This is the answer. So the real part of s is greater than 0. Basically some problem you may face about the solution of this. So basically we can write it as summation k is equals to 0 to infinity e raised to the power minus skt. We can put all these terms outside the integral, so it is minus infinity to plus infinity del t minus kt into dt. Now if we analyze this integral, then it is nothing but 1. The area of unit impulse is always equals to 1. So the remaining term is summation k is equals to 0 to infinity e raised to the power minus skt only. The remaining term is this, and the series expansion is basically the GP. It is the series is JP. It is GP. So an infinite GP. This is infinite GP. The infinite series is there. So the first term is 1, and common ratio is e raised to the power minus st. Then first term divided by 1 minus common ratio is the solution. And obviously that ROC is nothing but the real part of S. For convergence of this series, this real part of S should be greater than 0. The real part of S should be greater than 0. So because if we see that it is e raised to the power minus skt. So k is a positive quantity. It is varying from 0 to infinity. Capital T is constant. So if real part of s greater than 0, then this skt will become negative. And when we will put basically we can say that the series will always converge. Basically the series will always converge for real part of s greater than 0, and it will diverge for all other values of t. It will diverge for all other values of t. So let us solve another problem. That is problem E. So it is xt is equals to summation k is equals to, okay, so it is del I have written again the same question that we have solved before. So it is del at plus b, and what is a and b? So these are nothing but real constants. These are a and b are nothing but the real constants. Now we need to find out xs. So xs is nothing but minus infinity to plus infinity. According to the definition of Laplace transform, it is xt raised to the power minus st into dt. So it is minus infinity to plus infinity del at plus b raised to the power minus st into dt. Now put at plus b is equals to k. So we have a dt is equals to dk. We have a dt is equals to dk. So what we will get here? We will get dt is equals to dk divided by a. So if a is negative and a is positive, so better to take in mod form. So a may be positive and a may be negative, so better to take in modulus form. So we can write it in dt is equals to dk divided by modulus of a. So xs is written as minus infinity to plus infinity del k e raised to the power minus instead of t we have to write k minus b divided by a, k minus b divided by a, and it is dk divided by mod a. So instead of t we have written k minus b divided by a, and the solution of this is 1 divided by mod a e raised to the power asb divided by a. So the ROC is nothing but the all values of s. The ROC is all values of S. So we can solve this problem by using the property of unit impulse function, that is AT plus B. So it is written as it can be written as del A. If we take A common, then it is T plus B divided by A. Now if we find out the Laplace transform of this signal, so here what is going on, we have scaling and also we have shifting, we have time shifting. So basically this T is changed to T plus B by A, and after that this T plus B by A we did scaling. We are multiplying the A constant. We did scaling by multiplying by a constant of value of means a constant value A. So if we find out the Laplace transform, then we can directly find out the Laplace transform of del A T plus B by A. So what is the Laplace transform of this signal? So first we need to see find out the Laplace transform of. So if we need to find out the Laplace transform of del A T plus B by A, so what we can do, step 1, we can find out the Laplace transform of T plus B by A. So what is Laplace transform of T plus B by A? It is equal to e raised to the power SB by A into Laplace transform of del T. So it is equal to e raised to the power SB by A into 1, because Laplace transform of del T is 1. Now we can use the time scaling property, scaling in time domain property. So Laplace transform of A T plus B by A is 1 divided by mod A Laplace transform of del T plus B by A, and it is equals to 1 divided by mod A into e raised to the power SB by A. So we have applied that time shifting and scaling property, and we find out the Laplace transform of del AT plus B, and we find out the Laplace transform of del AT plus B. So the Laplace transform of del AT plus B is equals to 1 divided by modulus of A e raised to the power SB divided by A, and the ROC is entire S plane. So basically all values of S. So the ROC includes all values of S. So let us do the problem number 2. So in problem number 2, find out the Laplace transform of del T, then find out the Laplace transform of del dash T, then we need to find out Laplace transform of TUT, e raised to the power minus AT into UT, then T e raised to the power minus T into UT, then we have cos omega naught T into UT, and e raised to the power minus AT cos omega naught T into UT. So we need to find out the Laplace transform of these all these problems. So answer is we have xt is equals to del T. So the Laplace transform is xs, that is minus infinity to plus infinity xt e raised to the power minus st into dt, and it is minus infinity to plus infinity del t e raised to the power minus st into dt. Now it is minus infinity to plus infinity del t raised to the power minus s into 0, because the delay is here is 0. So we have applied the sampling property. Here. So this is a sampling property. So what we have to write is minus infinity to plus infinity del t into 1 into dt. It is minus infinity to plus infinity del t into dt, and we see that the area of unit impulse is always 1, so the Laplace transform of del t is 1, and the ROC is all values of s, that is the entire S plane. So the ROC is entire S plane. So let us do the part B, that is xt is equals to del dash t. Then the Laplace transform is xs, that is minus infinity to plus infinity xt e raised to the power minus st into dt, that is minus infinity to plus infinity del dash t e raised to the power minus st into dt. Now we can use the differentiation property here. So what is the differentiation property? So according to the differentiation property, we have ut, so we have del dash t. So how del dash t will come? So if we differentiate the unit step function, so del dash t is nothing but dut divided by dt. Del dash t is nothing but dut divided by dt. Now we can take the Laplace transform on both sides. So taking the Laplace transform on both sides, we get, because it is difficult to solve this integral, so because del dash t, because del dash t, if we have del dash t, then it is difficult to find out that value of this integral. So because del dash t difficult to find out value, we have one property I will tell you, and by using this property we can find out that integral also. But we can solve it efficiently by using this relation. So we have used del dash t, that is dut by dt. Taking Laplace transform on both sides, what we will get? We will get Laplace transform of del dash t, that is also equals to xs. It is equals to Laplace transform of dut divided by dt. Now we can apply the differentiation property. So what is differentiation property? Is telling that if you have if according to the differentiation property, if xt has Laplace transform xs, then Laplace transform. So if xt has Laplace transform, let take it as gt, it is better because we have already taken that xt notation. So if gt has Laplace transform gs, then dgt divided by dt, the Laplace transform is s into gs. So the Laplace transform of ut, we need to find out the Laplace transform of ut, and the Laplace transform of ut is 1 by s, and real value of s greater than 0. Then the Laplace transform of dut by dt is nothing but s into 1 by s. It is equals to s into 1 by s. So so basically the Laplace transform of del dash t, so what is Laplace transform of ut? The Laplace transform of ut is 1 by s, So the Laplace transform of